All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you're all having a good day today. The grade 4 class was a great success. Everything went well. I know that none of you actually really care very much about what happened in this grade 4 class, but the part that was the most concerning to me was that while the school has Wi-Fi, I didn't really have time to get Wi-Fi working on 11 tablets within the 1 hour that I had. My mic is indeed on. I've just put this little fluffy thing on here because I noticed that it clips quite badly when I'm talking, and I'm not sure if this will help or not, but I hope it does. But thank you for asking, yes. Didn't really have time to set up Wi-Fi on all these devices, and the microbit interface, so for what it's worth, this is at makecode.microbit.org. This interface will let you work offline. So the default thing, I've got this with JavaScript set up right now, or Python, but the default thing here will let you do this completely offline, which is really nice. So like once you load this thing up in the web browser, it just works. And everything went well, and so I'm really, really happy about that. And it's kind of a nice proof of concept that as a department, we can take these pixel tablets, connect them to these microbits, and take them around to schools and stuff for outreach activities like this. So I'm really delighted that it went as well as it did. So what I want to be able to do today in terms of operating systems is I want you to be able to explain how a process's an entire address space can be provided or supported via the concept of virtual memory. So this is going to be an ongoing thing. This is going to be an ongoing thing really for the next 3 weeks of classes, or 2.5 weeks of classes at this point. So the remainder of this course, we're going to be talking about virtual memory, and we're going to kind of be changing how virtual memory works as we go through the remaining lectures. For us, for today, what I'm looking for, and in terms of the stuff that we're looking at this week, I'm looking at this from a very high-level perspective. So going from the idea of there's exactly one program running on this machine at a time to there are multiple programs that are running on this machine at the same time, and they all seem to have their own independent idea of what memory looks like in terms of the addressable memory that they have access to. The other thing I want to begin to do today is to describe how the operating system works with the underlying hardware to manage paging, but really just generally virtual memory. So we're going to get to paging. I promise that we will get to paging before this class is done, not today, but before the course is over. But for right now, our focus is entirely on the idea of what does the operating system need to do in terms of how it changes its own internal structures. So what do we have to add to these internal structures? And then what does the operating system need to do in terms of like working with the hardware to actually do the virtual memory stuff? Later, we'll talk about what paging looks like in terms of things like the page table and page table entries, and what that needs to look like from the operating system's perspective. But for us, for right now, it's really just like what kinds of changes do we need to make to our data structures that we as an operating system are maintaining for doing this stuff. Let's do a quiz. Let's do a quiz right away. So I'm going to hold this up here for about 10 seconds, and then I'll switch over to the Mentimeter. All right, I'm going to pop over to the Mentimeter. The code should stay up there at the top of the screen as we're going through this. I'll give you about 10 more seconds to join. All right, so the first couple of questions that we're going to have here are about disk and I/O scheduling stuff first, and then we'll move on to more virtual memory related things. Just want to make sure that it's working for everybody. No, it's not. I'm going to forgive me, I'm gonna exit and then bring it back, but I'm gonna really politely ask you all to like put your head down for a second so you don't see the answer to the first question that I'm going to ask. Okay, all right, there we go. Okay, so yes, I'm very happy to see lots more people are joining up. Okay, so I'm going to start the quiz. Like I said, the first couple questions are about disk and I/O scheduling specifically, and then we'll move on to more VM-related questions. It messed up again. Well, 6 people were able to respond. I'll let this run out and we'll talk about this answer. Okay, all right. I'm gonna hit escape again and I'm gonna start this quiz and I'm gonna hit Control R and then I'm gonna start the quiz again. So when we were thinking about task scheduling, one of the policies that we were looking at was this shortest job first policy. And the shortest job first policy was not preemptive. It was not preemptive. And the way that this worked was that as new tasks came into the system, once the current task was finished, the task that gets to go next is the one that has the least amount of time attached to it. So the least amount of time in terms of we know in an unrealistic way how long this task is going to take. We changed that a little bit when we started to think about the shortest time to completion first, when we added preemption, but the idea was still there. We'll take a task off that happens to be long running, but we're going to schedule the task that has the least amount of time attached to it. In both of those cases, though, knowing how much time the task has left is unrealistic. So this was one of those unrealistic assumptions that we had about task scheduling. It's not really possible for us to know how much time is going to be left in a task in reality. But with I/O, with input and output requests, it is reasonable for us to have that. When I issue a read request, when I call the read system call, I'm explicitly saying how many bytes I want to read. I'm explicitly saying I want to read 30 bytes. You know how long that's going to take because it's 30 bytes. That's how much there is there that I want you to read. It's not read indefinitely, it's read 30 bytes. Likewise, if I ask you to write something, I'm explicitly telling you I want you to write 512 bytes, and you know exactly how many bytes you're supposed to put into this write request. As that drive is spinning really, really rapidly and moving that read head back and forth, it has to make decisions. Our drive will have to make decisions about which one of those sectors it's going to move to, and the policy that we were thinking about with that was this shortest seek time first. So depending on where my head is right now and the requests that are coming in, which one should I go for based on how long it's going to take to move the head to the correct location? Or do I just leave the head where it is and wait for this thing to fly under me and then move my head for the next one? Shortest seek time first was very closely related to shortest job first as a policy. Shortest job first as a policy was an unfair policy. It was not a fair policy, even if we could assume that all tasks are fair and that they would all finish. It was not a fair policy because we could get into this weird situation where we have a longer running task and then an infinite number of short running tasks that just keep getting added in front of it, and that long running task never gets to go. Shortest seek time first is the same problem. It's got exactly the same problem. If I keep getting requests for I/O coming into my system, but the time to seek takes too long to move to one other location on the disk, but I could just keep the head in the same place forever if this infinite stream of read requests comes in, then the policy itself is going to starve that one request. We'll never be able to get to that one request where we have to move the head. And so the shortest seek time first is an unfair policy in the same way that the shortest job first policy was unfair because of that one specific contrived situation. Okay, I'm going to move to the next question. I hope you are all still connected. I hope you are still, you're not. Right now, okay, just because I'm asking. I am indeed on U of M Secure. I resolved that problem. I'm actually able to connect to U of M Secure. I'm really hoping that the stream is not just freaking out right now. Are you able to connect now? Okay, awesome. Okay. I'm going to hit enter on this right away so that we can just hope that we can stay connected for this question. Awesome. Yeah, yeah. So, I mean, like we're talking about scheduling here, and surprise, it's a queue. It's not super surprising that we're seeing queues when we're talking about scheduling. So elevator, scan or C-scan, this is the idea that we've got that read-write head, and rather than trying to seek to the next thing that's closest, we just sweep all the way across, and we sweep all the way back, and we sweep all the way across, and we sweep all the way back. This is an elevator that's just going up and down in the building. And it's going up and down in the building, and then whoever presses the button to say, I would like to get on at this floor, eventually they're going to get access to the elevator because eventually it will stop on the floor because it's going all the way to the top and all the way to the bottom and all the way to the top and all the way to the bottom. Implicitly, this is building us a queue. This is implicitly building us a queue because we're going to keep sweeping across our disk, and the things that are closest to us right now are going to get to go first, yes, but as we sweep across the disk, we're going to service all the requests that came in that were farther away from our head at that point in time. So ultimately, this is implicitly building up a queue structure underneath, which kind of like ticket locks, I think is cool. We're building this queue structure without actually building a queue structure to represent these ideas. So this leaderboard is probably all messed up because of the getting disconnected, so sorry. Mars is way up at the top there, maybe because they're the only person that was able to stay connected long enough. I'm really happy to see that there's a grade 4 kid showing up because I cannot understand how they could possibly answer these questions after doing the basic stuff that we did last time. Are you all still connected to the quiz? Okay, good, yes. So we're going to move on from I/O related questions and start thinking about VM questions now. Virtual memory questions. All right, awesome. Yeah. So I want to be really clear that I think it's reasonable to have picked the code heap and stack regions because as far as we've been told in terms of like Comp 2280, and then even coming into this class, we've got the code region, we've got the heap, and then we've got the stack at the bottom. And when we're talking about address spaces, that's really what we're starting to talk about with those things. But as we grow up here in terms of just thinking generally about virtual memory, I want to generalize this now. I don't want us to think purely in the context of those 3 segments, in terms of those 3 named segments, because the reality for us is going to be that those 3 named segments are kind of coincidences, and they're like things that we've named but don't actually exist in reality in terms of the way that our virtual memory systems underneath are working. So very broadly, an address space is the addresses available to a process to use. On a 64-bit system, this is actually more like 48 total bits, maybe 54 total bits in terms of how much addresses a process is able to address. On a 32-bit system, it's quite small compared to that. But it's all of the addresses that are available for a process to be able to use. All right, okay. An operating system's responsibility in terms of virtual addresses is going to be, I need to add some information to my process control block. I need to add some additional information to my process control block so that I can configure the hardware when I'm going to context switch between two processes. When I go from process A and its address space, its virtual address space, to process B and its virtual address space, I want to be able to tell my hardware that it should use a different virtual address space. It should use a different mechanism for translating addresses. Converting virtual addresses to physical addresses happens purely in hardware, entirely in hardware. The operating system's responsibility with regard to the hardware is to tell the hardware, this is where address space starts for this process. The hardware, the memory management unit in this case, it is doing everything in terms of address translation. Our operating system could not reasonably do this. It cannot reasonably do this because for us to do things like access one location in memory would require like 3 different translations of addresses. And for our OS to do that, it would just add so much overhead for anything to work in a reasonable amount of time. So there has to be some kind of hardware support for this. Checking if a process uses unallocated memory. This one here is where we're doing things like if I've tried to access an address that I haven't allocated in my program, our outcome for us writing C programs is typically the word segmentation fault being printed to the screen. Our operating system doesn't check for this either. It can't check for this because it's not doing the address translations itself. Our hardware has the responsibility of checking to see if someone is accessing something that they haven't allocated or is not within the context of their address space. The operating system also has this responsibility, keeping track of free space in memory. It has the responsibility of keeping track of the allocated memory and thus also the memory that hasn't been allocated by processes, so the space that's available for it to be used for other things, for other processes. So to be clear, this part here, converting virtual addresses to physical addresses, this must be done in hardware. Our operating system is not fast enough to be able to do this with reasonable performance to accomplish this in the operating system. Does that make sense to everybody? We okay with that? Okay. Okay, all right. So I completely understand why you're picking the one in the middle, handling memory access exceptions. These two statements that I've got here, they are syntactically very similar to each other, but they semantically mean different things. Handling a memory access exception, to me, means doing something because it's happened. Doing something because it's happened, in our experience, has been our process gets killed and the words segmentation fault are printed to our screen. We're going to take this ride next week, but the hardware is not printing the word segmentation fault on my screen. The hardware is not printing that message to my screen. In fact, it's not even the operating system. We'll take that ride next week. It's not even the operating system that's printing that message. Handling the memory access exception in the context of an operating system's responsibility is, I'm going to take this task off of my task queue. I'm going to kill it because it is trying to do something that it doesn't have permission to do, or it's trying to access something that it hasn't previously allocated. The hardware doesn't know anything about our tasks. It doesn't know about the abstract structures between Windows and Linux and Mac OS. It just knows that there was a memory access request to an address that wasn't mapped. That's the only thing that it knows. It has the responsibility of keeping track of these exception handlers. And this is something that our operating system has the responsibility of doing, telling the hardware when there's a fault, when there's an exception in terms of accessing addresses, this is the code in the operating system that you should invoke. So when our OS is coming up, when it's starting the system, it's going to tell the hardware, this is the address that you should start running code in when there is an error related to memory. And it's the OS's job then to take over and actually handle the exception and actually deal with the try to solve that problem. The hardware here actually knows very little about memory. Modern hardware knows lots about memory, but in terms of the general idea of what we're thinking about, our processor knows hardly anything about actual memory in terms of what's allocated and what's not allocated. The closest that we're going to get to this is when we do start to talk about paging and when we do start to talk about the idea of page table entries referring to allocated structures. But even then, the hardware doesn't know much about the free space that we've got in our system. So the main responsibility here in terms of supporting address translation is having additional registers so that the operating system can set those registers when we do context switching, actually doing the address translations, and then when there's an issue that comes up related to address translations, knowing what to call in the OS, what to start running in the operating system so that the OS can actually do the handling of that exception. So again, this is a very syntactically similar response here, but they semantically mean different things in terms of what's actually happening. Is that okay with everybody? Okay. Mars is still at the top, holding on to that tightly, and Sub is showing up underneath that. And the gray 4 kid is still here, Okay. The last 3 questions, we're going to be asking a little bit about the layout of an address space and who's responsible for each of those different parts of an address space. So while I said code, heap, and stack don't really exist, I'm going to stand by that statement, but abstractly they still exist in the context of our code. And I want to start thinking about who has the responsibility of working with or managing or populating each of those segments. So here are the last 3 questions. Populating here, I mean to say like fills it up. Who fills up the code segment or the code section? Who puts the code in the code section? Okay, yeah, yes. So the operating system has the primary responsibility of loading this program up. So when we do like / something in our shell or run this command in our shell, we're asking the operating system to do exec, and the exec call is ultimately going to take the code from that file and load it into the code section. And that's going to be the responsibility of the operating system. I do want to point at this picture in the background. This is the front of an Altair 8800. This is way before my time, but I spend an embarrassing amount of time watching videos talking about old computer hardware, and so I have some idea of what's going on with this. These here are switches. They are literal switches that are up and down, on and off, and it's the responsibility of the operator to fill memory by going to address 0 in this system, toggling the switches correctly, and then pressing a button to say save this at this memory location, and move to the next one, and then toggling some more switches, and then pressing a button to persist it in memory at that location, and then toggling them again and pressing a button. So in ancient times, the person who was responsible for populating the code section were your parents, when they would actually have to switch toggles to set up our address spaces. But for now and for us, it's the operating system. Here's the next question. The order of these options are the same for the next 2 questions. So the options that you're going to see are the same, and they're going to be in the same order. Okay, all right, okay. So I guess I want to clarify what I mean by this part. The compiler here, in my mind, is what's responsible for ultimately causing the instructions that build the stack for us. And I want us to think back to what was going on in Comp 2280, where I believe you had to implement your own stack. Yes? Shrug? Maybe, yes. I think that this is a responsibility that you might have to do in Comp 2280. When you're doing it, you're writing instructions. You're writing LC3 assembly to do this for you, but the responsibility of emitting those instructions in x86 assembly for us is going to be our compiler. And so when we are running our code, it does definitely add stack frames and pop stack frames off as we return from functions. It's ultimately the compiler's responsibility to set up the code that causes those stack frames to be added and popped off as things are working through our code. Here's the last question, and you will be surprised by what the question actually is in no way whatsoever. Okay, good, yes, yeah, yes. It is our own program / the standard library. We're going to see this. I actually want to run code that shows that when we are doing malloc, we are not making system calls. We might make one system call, but we're making very few system calls. The operating system actually has very little responsibility in terms of managing the heap. The operating system's responsibility is to know what's been allocated in terms of overall physical memory. It doesn't give a shit about whether or not it's the heap. It really doesn't care. It has no sense of what the heap is as far as we're concerned. What we're ultimately going to see is that it's our own program. Yes, we call malloc and we put bytes into the thing that we've allocated 100%. But when I call malloc in my standard library, it's the standard library's job to figure out how big the heap is right now, as opposed to my operating system doing any of this for me. One of the things that we're going to see as we go into this is that we can actually switch out the allocator that we're using for malloc. So we can have different code doing malloc for us as opposed to the one that's built in by default. Some allocators never ask the operating system for space in the same way that we have been thinking about it. So it's almost entirely our own program, or almost entirely in the standard library or the allocator that we're using that, that does this for us. All right, let's see where we're at. Let's see if Mars's lead was able to stay up at the top. Whoa, someone took the lead from Mars. Okay, so congratulations, Sub, and congratulations, grade 4 kid, for working your way up to the top from the bottom there, and everyone else. Thank you all for participating. I mentioned this in the previous, not in the previous, in the other section of this class, and now I'm going to mention it to you. I have gone through like previous lectures where I have quizzes like this, where I've got answers and stuff, and I've linked to the Mentimeter slides in those lecture sections, and I plan to continue doing that. So for today, I'm going to put a link to these slides in today's lecture section, so you can access them with the correct answers marked if you want to see it again later. I only really thought to do this after I saw someone in the other section taking photos of the screen, and I didn't mean to hide them or anything. It wasn't intentional, and I wasn't intentionally hiding them. I just never thought to post them up on the course webpage. So I'll post a link to these slides that have the correct answers marked, and it will be up on the course webpage next to the actual slides for today's lecture. All right, okay. So I want to talk about virtual memory. And what I want to do with virtual memory when I'm thinking about this is kind of think about computer memory in general. Have we seen this diagram before, or something that's shaped like this diagram before, in terms of the kinds of memory that are attached to computer systems? Okay, all right. So this thing is called the computer memory hierarchy. I'm going to pop this open, and I'm going to make it quite a lot bigger because it's hard to see in that little thing. This is a triangle-shaped diagram, and this triangle-shaped diagram represents at the very bottom the biggest volume of memory. And as we go down on this diagram, we also go down in terms of cost. So at the very bottom, we've got persistent storage. So these things that say power off, there's 3 of them there. These are power off, and they are going to be persistent storage. After the machine has turned off, they will retain what they have on them right now. At the very, very bottom here, we have this long-term kind of archival storage system. And modern systems, in terms of long-term archival storage, will use tapes. They will actually use tape still. Tape is the way that you back up terabytes and terabytes of data for long-term storage. Tapes are real slow. They are really, really slow because you literally have a tape that is on spindles that has to like move around for you to be able to put stuff on it. But it's also really, really cheap per terabyte. Like, we're talking about like cents and dollars per terabyte as opposed to tens of dollars per terabyte. Hard drives show up beneath that, and these two, in my mind, are starting to get closer to each other. Hard drives, we're now talking about capacities of like 24 and 30 terabytes for a single hard drive. They're getting to be very big, but they're still more expensive per terabyte than tapes are. But in terms of our thoughts of how fast things go, hard drives are still quite slow. Hard drives have response times of things like milliseconds here, which is, compared to the speed of our processor, an immensely long time for something to take to be able to satisfy a request for I/O. I don't actually know why USB memory appears before hard drives, because USB chips are usually pretty slow compared to hard drives. But flash. So when they say flash here, what I'm thinking about is stuff like NVMe and SSD disks. They are faster than hard drives. They are still slow compared to a processor, but they are now more expensive than what we have for hard drives. Then we get to RAM. And RAM here, this is where we're going to be dwelling in terms of thinking about virtual memory. Virtual memory, to be clear, goes all the way down to the bottom, even 2 tapes when we start to think about swapping, but we're not going to talk too much about swapping. We'll stick close to RAM here in terms of virtual memory. And then when we're getting to the very, very top here, we're talking about things like processor registers. These are things that are on the order of like 4 bytes in size. So a 64-bit register is 4 bytes, 8 bytes. It's 8 bytes. It's 8 bytes. 64 bits is 8 bytes. We've got an 8-byte register here that is crazy fast compared to a processor, so like nanosecond access times. The idea with all this is that we have a small amount of memory that costs a lot of money that's really, really fast. And at the very bottom of this hierarchy, we've got something that's really, really big, very inexpensive, but super, super slow compared to what's at the top. Virtual memory is ultimately going to let us start to think about things like having all of these be within the same sort of address space, sort of, in a really, really hand-wavy sort of way. Here are some other things that are shaped like triangles. This is Bloom's taxonomy. Bloom's taxonomy is something that is used when we're teaching people about stuff in terms of their ability to either synthesize new things, evaluate things, being able to do things like, I'm going to memorize this thing on a test. So this is at the very bottom of Bloom's taxonomy. In 3rd and 4th year courses, we're trying to get closer to the top of Bloom's taxonomy as opposed to the bottom, where this is usually where you are in like grade 4, when you're in grade 4. Another triangle-shaped thing are the pyramids. I'd really love to go see these someday. I think that that would be cool to go see the pyramids. I don't think I'm going to get to them anytime soon, but I'd really love to go to see them in Egypt. Pyramids are triangle-shaped things, and that triangle-shaped thing on US money is also a pyramid, and it's triangle-shaped. And the Bermuda Triangle is also a triangle-shaped thing. And finally, the flag of Nepal, it has 2 triangles in it, and so I think that's an impressive thing. The memory hierarchy is a triangle-shaped thing. At the very top is fast, expensive, and small at the very bottom is really big, very cheap, but very slow. I want to start thinking about address spaces. I want us to start thinking about virtual address spaces. And I want us to think about trying to see what's actually happening in the context of a running process. So the diagram that I've got here, this is a figure that comes from our textbook that describes what an address space looks like in terms of the different segments that we've got in our virtual address space. I want to see if we can make observations about the address space that a process is able to see by doing a couple things. I first want to run some code. The code that I'm going to run is called addresses.c, and it's in this linked Git repository. I linked to this also on the course webpage if you want to have a copy of this on your own machine. You should be able to run this code on any of Mac OS or Linux. This is not doing anything special. This is just taking a look at some addresses of stuff that happens to be in memory. So I'm going to start by popping over to my terminal here, and I'm going to open up addresses.c. Addresses.c really just gets the addresses of some things so that we can try to see what the overall layout of our virtual address space is for this process. So the first thing that we're getting here on line 10 is the address of the main function. This should approximately be somewhere in the code section. This should be in the code section. This is going to be the address of where our main function starts, and this should be somewhere in our code section. On line 15 here, I'm taking the address of the variable that I just declared, and that should give me something that's on the heap. So where the address of the main function is in my code section, this is the actual code that I'm executing on the CPU, the address that I've got for this variable, it's a stack allocated variable, so it should be in the stack region somewhere. Is that okay with everybody? Okay. On line 19, this is the last region that I want to test. I'm going to do malloc. I'm going to ask for 1 byte, and the address that I get back from malloc ought to be in the heap somewhere. Once I get those addresses, I'm going to print some of this stuff out. I'm going to confirm that the address space is what I think it is. So I'm going to use a cert to verify the addresses are relative to each other, that the code section is at the top, the heap is beneath it, and the stack is at the very bottom of memory relative to each other in terms of the layout of our address space. So I'm trying to experimentally confirm that the address space that we think about is actually what we're seeing in the code that we've got here. The last thing that I'm doing here is just doing get char. I'm just blocking this process so that we can start to inspect things about it using some other mechanisms. So I'm going to quit this, and I'm going to make it, and I'm going to run it. So the addresses that we have here are the main function is somewhere up there at 55F153DF7180, which is a very big number. It's a very, very big number. I'm able to also see now that the stack is pretty close to it. It's pretty close to it in the sense that it starts with the same prefix, so 55F1. After that, they deviate, and I'm expecting them to be some distance away from each other. The code section should have some code in it, and there might be other stuff in it before the heap is able to start. At the bottom of my address space is my heap, and this is a really big number, a really, really big number. 7F is going to be much, much lower than that. Yeah. The stack is at the bottom of my address space. Thank you. Thank you for the correction. I meant to say that this is the stack. Yeah, this is supposed to be the stack, and the stack is at the very biggest address that I've got, so it's closer to the bottom. I'm going to hit enter, and I'm going to run this again. And I'm going to hit enter, and I'm going to run this again. And I'm going to hit enter, and I'm going to run this again. Relative to each other, these segments are always in the same general location, relative to each other. But they're not at exactly the same location. They aren't at exactly the same location, which is maybe a little bit baffling because it's a code segment. It should be at the same place every time I run this program. My stack should be all the way at the bottom every time, and it's around the bottom. It certainly is around the bottom, but it's not exactly at the highest possible address that I've got in my system. I'm going to pop up another window here. This is a virtual machine that I'm running. This is Ubuntu 4.10. So this is about 20 years old in terms of the operating system that we're using. On my actual laptop here, I am running kernel 6.11, so that's fairly recent in terms of Linux kernel releases. The Linux kernel release that's being used in here is 2.6, which is significantly older. It's significantly older. This is a 32-bit operating system right now. So the addresses that we have in this 32-bit operating system are much smaller. There's a significant number of bits fewer from 64 to 32 bits. That feels like a very thank you, Captain Obvious sort of statement. I've written this code again because I could not install Git because none of the repositories work for this system anymore. And I couldn't wget from our Git repository because the certificates that it uses for connecting securely are also wildly out of date on this operating system. So I rewrote this. So to be clear, it's different. I don't have the comments in the code that I've written here, but the actual function of what I've written is identical, the code that does the actual address stuff. So I'm going to make addresses here. I think it's already made, and I'm going to run it. And I'm going to hit enter, and I'm going to run it, and I'm going to hit enter, and I'm going to run it, and I'm going to hit enter, and I'm going to run it, and I'm going to hit enter. And this time the addresses are all identical every single time I run this program. They are still kind of correctly relative to each other. I still have my code segment at the top. I still have the heap beneath that, and the stack has the highest set of addresses that I've got here. When you try to run this code on your own system, and when you try to run this code on Aviary, your output is going to look more like what I was showing you in my own terminal, where it's changing the address every time. The result that we're seeing there is something that's called address space layout randomization. This is ASLR, address space layout randomization. And the idea is that this is meant to be a security mitigation. An attacker cannot cause code to run if they don't know where that code is. If you can't predict where the stack actually lives relative to the heap, if you can't predict where the actual location of the heap itself is, you can't overwrite values that are in there by hard coding an address in the same way that you might be able to here. This is a minor bit of trivia in terms of us, in terms of thinking about things, but the idea here is that every time my code runs for every single process on my system, the address space is going to be slightly different from the other processes that are running on my system. But that's kind of a coincidence in terms of the security mitigation that's happening here. So I'm going to pop back over here, and I'm going to run addresses one more time here. So what we've got here is a listing of approximately where these different code segments are in the virtual address space for this program that's called addresses. I'm going to pop open a terminal to the side here, and we're going to go to the proc file system. Remember the proc file system here? This is a folder structure that represents all of the running processes on our system. So there's folders here that have process IDs for their name, and then within these folders are going to be information about that running process. So I've printed out what the PID of this process is, and so I'm going to change into that directory in the proc file system. And within that, there's going to be a bunch of additional information here that represents the state of this running process. The file that I'm interested in taking a look at right now is called maps. Maps is going to be a mapping of the virtual address space for this process to different files and different parts of memory. So I'm going to zoom in on this, this tab here, and I'm going to take a look at maps. I'm going to just make this a little bit smaller so that it's visible here as a high-level structure, and I'll zoom in to see what these things actually say in a moment. But what I want us to be able to see is that we've got up here a code segment. This part is the top of my virtual address space, and what I've got mapped to that location is the program. This is the program that's called addresses that's been loaded into that code section of my address space. It's being loaded repeatedly, so this is going to be different copies of the same code loaded into different places that has different permissions that are attached to it. So these here are going to represent the permissions that are on that specific range of memory that's been allocated for this process. The code section has to have things like I have to be able to read it and I have to be able to execute it, but I don't really want to be able to write it. Beneath that here, and I can stay zoomed in, this is our heap. This is the heap segment that's been allocated for this process. And these are the address ranges that we've got for that heap segment. At the very bottom of memory for this process, here is the stack. There's other stuff that got loaded into our address space by our operating system, but we've got the three major players here. we've got our heap at the top, we've got the code at the top, we've got the heap beneath that, and then we've got the stack at the very, very bottom of this. We'll come back to this on Friday. We'll take another quick look at this file to get a little bit more sense of what's going on in there. But what you should be able to do at this point is you should be able to approximately explain how an entire address space worth of memory addresses can be fit into an actual system with the concept of virtual memory. You should have some idea of how the operating system works with the underlying hardware to manage virtual memory. That's it for today. I hope you all have a good day, and I'll see you all on Friday. Bye, everyone.